Okay, well, thank you, Abraham. It's a pleasure to be here. You know, there are lots of different ways one could imagine giving a talk in honor of Bob Ullman. There are so many things to honor. And I decided to take as my inspiration for this talk a paper that Bob wrote in 1985 called "What is Game Theory Trying to Accomplish?" And he, I think it turns out, had great foresight. He was also very optimistic about the future of game theory. And part of this optimism about game theory is what has allowed, part of his optimism about game theory is what has allowed all of the rest of us game theorists to sort of flourish under the protective umbrella of his confidence that game theory would be a good thing to do. But in 1985, it was still pretty early days for game theory. And the way he organized his paper, along with some general thoughts about science and how to do it, was around some particular game theoretic solution concepts. He talked about the Nash equilibrium and the core, and I'll talk about those today as well, and also about the von Neumann-Morgensterns and the Shapley solutions, von Neumann-Morgenstern solutions and the Shapley value, which I will not talk about today. And rather than putting at the, for my talk today, rather than putting at the center of game theory the various solution concepts, I think what I want to suggest to you is the big thing that game theory did is it put the rules of the game at the center of economic models. So when I was a young man getting my PhD, if you met an economist who said he was a theorist, what he meant was he did general equilibrium theory. He thought about prices. And often we thought quite carefully about commodities, about what kind of commodities were being sold. But after that, the rules of marketplaces played very little role. There was this idea that markets consist of the supply and the demand, and prices appear somewhat magically. But game theory gave us an opportunity to look at the rules by which marketplaces are designed. And design is a noun as well as a verb. I'm going to tell you about market design as a verb a bit today. But one of the things game theory allows us to do is look at the rules by which marketplaces are organized. They are its design as a noun. And for game theorists, rules are data. Some rules work well and some rules work badly. And what market design is about is helping fix markets whose rules are working badly. Because markets are human artifacts. They are things that we build, and when they aren't working the way they should, we should fix them. So in Ullman's article, when I'm quoting Ullman, you can tell I'm quoting him because of the picture. He said, you know, game theory and the real world, it might better be called the complex world, have a relationship that is not entirely comfortable. And part of what he was talking about is what we value in theory is simple, elegant models. But the world is complicated and messy. And so one question is how to think about the relationship between simple, elegant models and the messy, detailed world. And so the point of view that I'm going to take today is talk to you about market design as a kind of economic engineering, and suggest that in general science and engineering have different relationships to the complex, detailed world. And you know, there's an old joke that says in theory and practice are the same thing, but in practice they're not. Science and engineering aren't exactly the same, but they complement each other, but they work on different time scales. You know, science aspires to be eternal, and engineering is ephemeral. So let's think a little bit about Pythagoras' theorem, right? It's a theorem about right triangles in the time of Pythagoras and also today, in ancient Greece and also in modern Israel. Anytime you meet a right triangle, you can tell it about Pythagoras' theorem. But engineering isn't like that. Bridges have been built for a long time. Here's a Roman bridge. It's a great bridge because it's still standing. But modern bridges today, you know, here's Gesher HaMitarim, the biggest egg slicer in the world, you know, is a very different kind of bridge than this Roman bridge. Partly it's different because we learned a lot from building bridges, how to build them better. Partly it's because we need different kinds of bridges. The Romans never built any rail bridges, right? They didn't have railroads to deal with. So the environment for which bridges are needed changed, but also our knowledge of how to build bridges. You could not, you know, a Roman engineer might have understood some of the principles that hold that bridge up, but he certainly didn't command the technology that would allow him to build it. So we learn a lot about building bridges by building bridges. We also learn a lot about building bridges from bridges that fall down. Okay, so here's a famous picture of the Tacoma Narrows Bridge. You may have seen videos of it twisting in the wind. It fell down because it resonated to the wind, and that broke it. And here's a more modern bridge failure here in Tel Aviv. I understand there was a river failure as well at the time. So I am going to tell you about some broken bridges. I'm going to tell you about some rules of marketplaces that didn't work well and how we learned to fix them. And I'll tell you about the theory, the game theory that we had available to us at the time that we fixed them, but also of some things we learned from building the new marketplaces and how that has led today. I'll show you some quite recent game theoretic results, some 21st century results that we learned from the process of building these new bridges, these new markets. And in particular, I'm going to tell you about a market design set of events that I was involved in starting around the time that Bob wrote his article on what is game theory trying to accomplish. So I started to study those markets in the 1980s. And I'll tell you about some successful designs and how, as the technology of educating doctors changed, how those old designs stopped working so well and needed to be fixed. In particular, I'll tell you about how we now handle married couples. You know, when the doctors first developed the marketplace that I'll tell you about, all American doctors were men. Today, half of American doctors are women, and some newly graduating doctors are therefore looking for two jobs, not just for one. And I'll tell you about how the marketplace had to be adapted for that. If there's time, I'll also tell you about some school choice design that we've been involved in the United States. There's some going on in Israel as well. There's also some recent design by Israeli market designers of the first market for Israeli doctors. That doesn't look so good. Okay, so let me tell you a little bit about the market for doctors, starting at the turn of the last century. So that's when the standard first job, that's when what is now the standard first job for doctors became standard. Doctors do what's called an internship and residency after they graduate from medical school. So the first job of a doctor is at a hospital under supervision of more experienced doctors. And today, to get licensed as a doctor in the United States, you have to complete some parts of a residency. In 1900, the way you got this job is you graduated from medical school according to the normal academic calendar and started to look for a job. And the job would start in July, right after your graduation. And so you looked for jobs in 1900 shortly before you graduated, jobs that you would take after you graduated. But one of the ways hospitals competed with each other for good interns and residents was to advance the date of appointment, to start hiring them earlier. So by around 1930, doctors were mostly being hired not just before they graduated, but around the winter holidays of their last year of school, so about 6 months before they graduated. And that process, if you look at the medical journals of the time, the doctors, the employers, the hospitals regretted this. They said, you know, this way, now we're hiring people without knowing their final grades and their standing in class. We can still manage, but we shouldn't hire any earlier. Well, needless to say, the incentives that made some hospitals hire earlier than others didn't go away. And so by 1940, the customary time at which doctors got their first job, which they would take after they graduated from 4 years of medical school, the customary time at which they got the job was after their second year of medical school, 2 years in advance. And this caused lots of inefficiency. You could imagine that it's hard for the hospitals to tell who are the good doctors, but it's also hard for the medical students to tell what kind of doctors they hope to be, and therefore what kind of first job they would like to have. So there was lots of inefficiency. And around 1945, the medical schools, who are a third party, they're not the doctors and they're not the hospitals, they got together and agreed not to give out any information before a certain date, so to make it hard to hire doctors too early. And that was successful. And over the years 1945 to 1950, they successfully moved the time of contracts being signed from the end of the second year of medical school into the fourth year of medical school. But they had a lot of other troubles then. They had a lot of exploding offers. They still had a lot of mismatches. I could tell you more about that story, but that's not my story today, except to say that the market was not working very well. It was a failed bridge. They all understood that the market was working very poorly. And then they did something quite remarkable. they developed a new market design on their own, largely through trial and error that had been going on in smaller markets over the years. They developed a centralized clearinghouse, which had some very good properties, which I'm going to tell you about. The design of their market had good game theoretic properties. But in particular, it had high rates of orderly, voluntary participation. Instead of having this chaotic market where offers were made one at a time and you had to respond before you could learn what other offers were coming, after everyone had gone on interviews, after the hospitals had interviewed the graduating doctors, they asked all the doctors to voluntarily submit to a central clearinghouse a rank order list, my first choice job, my second, my third. And they asked the hospitals to do the same thing, of the people we interviewed, who's our first choice, who's our second choice, who's our third. And then they did something, and I'll tell you about the something that they did. They did something to combine this information and suggest a matching. And they got very, very high rates of participation. So that 95% says that for a long time, for 20 years following this innovation, when you looked in July at where doctors were, they were where they had been matched. So almost all doctors and residency programs participated in the match and then went, when they got a message that said, here's where you've been matched, proceed to sign a contract. And in 1950, the percentage of women graduate medical students in the United States had been roughly 0%. By 1970, it was 10%. And medical students are, of course, very, very busy, but one of the things they can find time to do is to marry each other. And there started to be married couples on the market. And one of the things that you could observe in the 1970s, starting in the 1970s, was that the married couples were not going where they were matched. Either they were not participating in the match or they were getting suggested matches and then that's not where they were in July. They were showing up with jobs at other places. And I will tell you in a moment about how the medical authorities tried to handle that. They understood that they had a market design problem and they tried to change the market to make it more friendly to couples, but they were unsuccessful. So this was also a failed bridge. And as the percentage of women medical schools grew to 50%, which it is now, and the number of couples grew, so we now have around 17,000 medical graduates a year in the United States, and more than 1,000 couples go on the market. More than 2,000 people of those 17,000 go on the market as couples. What they observed is that the couples were not participating in the match and that this was causing ripples that made it difficult for others to participate in the match. And in 1995, I was asked to help redesign this market so it could accommodate couples and some other things as well. So that's the story I'm going to tell you. And I'm going to tell you about what kind of game theory we had going into that, what we understood about the design of the existing market and what its failures were. And then I'll tell you some things we learned from building that marketplace without knowing fully how to explain them. And now I'll end this part of the story by telling you some modern game theory that explains clearly what it is that what we observed, what we learned from observation and practice. Okay, so let me go back to the beginning and suggest to you that what might make a clearinghouse successful is that it produces a stable match. And by a stable match, I mean a match that there isn't a doctor and an employer, a residency program, not matched to each other who would both prefer to be matched. And for a clearinghouse, you can see why it might be important if you're suggesting matches that you suggest stable matches. Because supposing the clearinghouse tells you you are matched to your third choice hospital, please go ahead and expect a contract from them and sign it and send it back to them. If you're matched to your third choice hospital, you only have to make 2 phone calls to find out if there's a residency program that you would prefer, either your first choice or your second choice. Those are the ones you prefer to your third choice. You have to only make 2 phone calls to find out if one of the ones who you prefer also prefers you. And if they do, then maybe you can sign a contract with them instead of the one that the match suggested. But if they don't, then you can't do any better than to accept your contract from the match. So you can imagine that if there were blocking pairs, we might not see such high rates of participation as we saw again now and in the early years of the match. So here's a hypothesis. How can we test it? Well, one part of the story I'll tell you is that the algorithm that the National Resident Matching Program produced in 1951 does produce stable matchings. I'll make very clear what I mean by that. But another thing we can do is we can look at other marketplaces. And the ones we had available in 1995 when I was asked to redesign the medical match were a small set, but what we could say about them is whether they produced stable matches or not, and whether they were still in use. So it's a very small set. Incidentally, when I say that rules are data, what I've got in the first column is whether the clearinghouse in that row produces a stable match in terms of the stated preferences, in terms of the preferences that are submitted to it, which all the game theorists in the audience know might be possibly different from people's true preferences. So we're going to have to come back to that to understand why it is that stable matchings work as well as we do. Because what you can see, if you have a willing eye, is that yeses in the first column seem to be associated with yeses in the second column, which tells whether the marketplace is still in use or whether it failed to stop unraveling and stop being used. Now I say if you have a willing eye because there are some, well, there are yeses and noes with noes. There are some yeses with noes. There's a failure in the gastroenterology fellowship market some years ago that's since been fixed. I don't think I'll have time to tell you about that today. But there are also some noes, the London Hospital and Cambridge, that weren't stable but are still in use. These were very small markets that dealt with a single hospital and the graduates of a single medical school. And it's possible they were a separate story. But when you have a small data set like that you're not quite sure what's going on, one of the things you can do is you can bring it into the laboratory. One of the tools of market design, along with game theory, is experimental economics. When you bring it into the laboratory, you can turn on and off whether the market is stable or not. In particular, in this experiment, we looked back at those markets in blue are a sort of natural experiment that involved the British National Health Service. Some regions of the British National Health Service, when they had a similar problem to the Americans in the 1960s, they tried to do what the Americans did, which is have a centralized clearinghouse. But each region of the National Health Service designed its own clearinghouse, its own marketplace. And some of them were stable and some were not. So in the experiment, we compared the stable Edinburgh 1969 algorithm, which I'll talk to you about, and the Newcastle algorithm. So let me tell you how those worked. Okay, how unstable matching mechanisms work, because that'll give you, right, this is a failed bridge, right? I mean, this is going to be a bridge that fell down, and that will give us some insight into what's wrong, what makes some bridges fall down. So here they were in Newcastle and Birmingham and Sheffield, and they had to make markets for their doctors, and they were having the same problems that in the 1960s that the American markets were having in the 1940s. That is, matches were being made very early. Right? Long before students graduated from medical school, they were being approached by consultants. That's the name for senior British doctors who were the employers, and they were being hired as house officers, their name for residents. So they decided, they were told by a royal commission that they should do what the Americans did and have a centralized clearinghouse. They should ask the doctors to give rank ordering of the jobs of the consultants, and they should ask the consultants to give rank orderings of the graduating doctors. And then they would use that information to produce a match. The algorithm, the design of their marketplace, the way they produced the match, was they did it in what they called priority matching. If a student and a doctor each ranked each other first, they were first priority and they certainly got matched. Okay, so they looked for 1-1 matches, and wherever they found them, that's where they matched people. Then they looked for 1-2 matches, student's first choice with doctor's second choice. And they matched all the ones they could find of those. And then 2-1. And then 1-3 and 3-1. So loosely speaking, they're prioritizing matches according to the product of the ranking. And when matches have the same product, 1-3 and 3-1, they have to decide on how to tie break. But you can think of this as they look at the product and they match all the 1s first, and then all the 2s who weren't yet matched, and then all the 3s and so forth. Well, what's wrong with this? What's wrong with this is it produces lots of blocking pairs. It produces unstable matchings. Why is that? Supposing you are the 4th best surgeon at my medical school, and I would like to be a surgeon, so I'm going to apply to you for a job. And because you're the 4th best surgeon at my medical school, I'm going to rank you 4th. First I rank the 1st best surgeon, then the 2nd, then the 3rd, then you. You're great. I'd love to work for you. And I'm the 4th best surgical ambition medical student in my medical class. So you rank me 4th. right? You'd love to have me work for you. But first, your first choice would be the best student, then the second, then the third, then me. You and I have priority on the order 16. Our product is 16. We are never going to be matched to each other. Instead, somebody who you liked much less than me, someone who ranked you 15th, someone who you ranked 15th, but who ranked you first, is going to be your resident. Okay, so you're really unhappy with your 15th choice resident. And especially when you notice that your 4th choice resident, that's me, I'm off in the Orkney Isles setting broken bones because my 15th choice ranked me first. Okay, so these jobs belong to the National Health Service. There's nothing we can do about it. But you, as a medical professor, you now go to the people a year ahead, who haven't graduated yet, and you say, look what happened to Al. He was such a good student, and he got such a bad job. Why don't you and I agree that next year we'll rank each other first? You'll be my resident. And you say, yes, sir. And this is a relationship. I mean, you're going to practice medicine in the region of your medical school, so this is a reliable agreement. And in Newcastle, after 3 years, they abandoned the scheme when they noticed that 80% of the rank orderings they were getting were simply 1-1 matches. That is, all of the matching had already been done before the lists were composed. People had reached agreements to match with each other and were merely ratifying the agreements using the match. And of course, this worked to the disadvantage of those who didn't teach at the medical school and who didn't know you were supposed to make early agreements and so forth. So this is a failed bridge. It didn't succeed in moving later the time at which appointments were really made. Appointments were still being made a year in advance. They were just being ratified through this mechanism. So it turns out, before that, independently of all this work on medical matching, the late David Gale and Lloyd Shapley had written a famous paper called College Admissions and the Stability of Marriage, in which they proposed a way of processing preference orders like this that would always produce a stable match. This is the deferred acceptance algorithm. And the way their algorithm worked is you have the workers submit preferences, you have the firms submit preferences, and in the worker applying version of their algorithm, there's also a hospital offering version. Each worker starts off applying to his or her top choice firm, and each firm that has, say, 5 positions holds on to the top 5 applications it gets and rejects the rest. But it doesn't accept the top 5 applications now. It's going to defer acceptance until it sees who else will apply. And who else applies is everyone who was rejected from their first choice now applies to their next choice. So each hospital that might be holding some positions now gets some new applications, some of which it may like better than applications it got before. So it keeps the top 5 it's gotten so far. If it's got 5 positions, rejects the rest. Everyone who's rejected applies to their next choice hospital that hasn't yet rejected them. And each hospital updates whose applications it's holding on to and who it rejects. And the algorithm only stops when there are no further applications, and at that point they accept the applications they're holding. And that produces a stable matching. And the way you can see it produces a stable matching is that if you're a hospital and I'm a worker and you are matched to someone you like less than me, you can be sure that I don't like you more than who I'm matched to, because if I did, I would have applied to you. Okay, the reason you don't hold me if you like me more than someone you're holding is that I never applied to you, and that's because before I got to you on my preference list, my application was held. Okay, so it produces a stable matching. This is the first of 2 remarkable theorems that Gale and Shapley proved in their 1962 article. Stable matching exists for every matching market, and in fact, it's produced by the deferred acceptance algorithm. A stable matching is, and the particular matching produced by the deferred acceptance algorithm actually has the special property that it's preferred to all other stable matchings. It's liked at least as well as all other stable matching by all the workers, all the ones who are active. And of course, there's another version of the deferred acceptance algorithm where the hospitals go down their rank order lists and make offers, and the workers hold on to the best one they've received so far and reject the rest. And that produces a hospital optimal stable matching. That's going to be important later when I talk about what's the size of the set of stable matchings, because all the stable matchings live in between the worker optimal stable matching and the hospital optimal stable matching when preferences are strict. And for labor markets, it doesn't do terrible violence to assume that preferences will be strict. So that was in the 60s. So in the 1950s, the doctors also invented an algorithm like this in the 1950s. In the 1960s, Gale and Shapley explained it to the game theorists without knowing that these parallel developments had occurred. In the 1980s, there started to be more game theory associated with these models. And in particular, there were started to be questions about incentives. Supposing you are a medical student and you are asked to give your rank orders. Is it safe for you to confide in the medical system what's really your first choice, what's really your second choice, what's really your third choice? And that's a good question to ask, because no stable mechanism makes it safe for everyone to state their true preferences. There's always the possibility that someone could do better by writing down different preferences than are his true preferences. Your true preferences are the ones you use to tell whether you got a good job or not. But the way to get a good job might not be to say what's really your first choice. But it turns out that when the workers are doing the proposing, it's completely safe for the workers to state their true preferences. They can't do better than to simply decide where they would like to go and write that down as their preference list. But it's important to remember that there's no way to make that also true for the hospitals. Okay? So it's a little complicated issue. We've created a game, and games are played. And if you're the director of a residency program, you might have some reason when you evaluate students not to list students simply in the order you like them. You might want to also take into account who else likes them and what your chance of getting them is and things like that. Okay, so this is a complex world, and I'm going to start as the world itself gets more complex as couples come into the market. Okay, so as I mentioned already, in the 1950s, doctors were men in the United States, and today only half the doctors are men. But in the 1970s, they could tell that that the marketplace, that worked much like the deferred acceptance algorithm that I just showed you. That's one of the things I discovered when I started studying these markets in the 1980s. They discovered that market didn't work well when not all the agents were looking for just one job, when some of them were married couples looking for two jobs. So they tried to accommodate these married couples who they were losing. They could see that the married couples were not participating in the centralized marketplace, and therefore increasing number of jobs were being allocated outside of it, which caused some coordination failures, not just for married couples, but for people who might have applied for those jobs within the matching clearinghouse and then discovered that they weren't really available. So here's an initial couples algorithm that the doctors invented in the 1970s. And whenever I think about this algorithm, I remember just how long ago the 1970s were. So let me tell you about this algorithm. To go through the algorithm as a couple, to go through the doctor match, the doctor labor market as a couple, first you had to be certified by your dean as a legitimate couple. Okay, so your dean had to think you were a couple. So in particular, you had to be a married heterosexual couple. Then they had to specify one member of the couple as the leading member. Okay, so the couple has to decide who is the leading member of the couple. Then they each submitted a rank order list that had the same grammar, the same format as if they were single individuals. That is, the format for each of their lists was, this is my first choice, this is my second choice, this is my third choice, and so forth. Then the leading member went through the match and hopefully got a job somewhere. Then the other member, never named, but the one who isn't the leading member, had his or her list edited to take out any jobs that weren't in the same city as the leading member. And then he or she went through the match, and often they were able to get two jobs in the same city. But it turned out they still didn't show up at those jobs. This was a nice attempt to help them, but when you looked at where people were, the couples were not in the jobs to which the match had assigned them. They were somewhere else, and that meant that some people who were supposed to get contracts, some single people who were supposed to get contracts didn't get them because those jobs had been filled outside of the match. So what's wrong? What's going wrong here? Why isn't this working? They often manage to get couples jobs in the same city. Well, getting jobs in the same city doesn't capture well enough what couples want, right? The iron law of marriage is that you can't be happier than your spouse. So think about me and my wife trying to get two jobs. Our first choice is two good jobs in Boston, say. And our second choice is two good jobs in New York. And our third choice is two particular good jobs in California. So when we went through the 1970s couples match, what happened is, supposing I was listed as the leading member, and I get a good job in Boston. Then they edit my wife's list to take away all the jobs that aren't in Boston, and she gets a mediocre job in Boston. Well, you can't be happier than your spouse, so we get on the phone and we call up our second choice, which is 2 particular good jobs in New York, and we say to them, you know, we got matched in Boston, but we had always had the ambition to work with you guys in New York. Do you have positions available? And they look at who they've been supposed to send contracts to, and they see that they like us better. These are 2 different jobs in New York, and they each like us better. And they say, you know, we just got an extra position. Why don't you, we'll send you a contract. And then they call up someone else and they say, bad news, you know, our dean, you know how deans are. We have 1 fewer position than we anticipated. We can't send you a contract even though we were matched. So we form a blocking pair, a more complicated kind of blocking pair than when they were just single individuals. But the deferred acceptance algorithm, which made sure to get stable matchings in terms of single people, was no longer getting stable matchings in terms of couples. So this was also a failed bridge. It didn't bring the couples back. So it turns out the problem is harder than that, because even if you ask couples for pairs of preferences, even if you can't possibly give couples what they want if you don't say to them, you need 2 jobs, tell us what's your first choice. Tell us the 2 jobs that are your first choice. Tell us what's your second choice. Tell us the 2 jobs that are your second choice. You can't hope to give them the jobs they want if you don't ask them that question. But even when you ask them that question, it's no longer true that a stable matching always must exist. So I actually wrote about this in a 1984 paper when I studied the design of the medical match. And in those days, I wasn't yet a market designer. I was just a theorist. So I had a counterexample which was sufficient. I could say this is a hard problem. The problem of couples is difficult. And I could stop there, right? I had a counterexample that showed you couldn't always find a stable matching. So I still have a visceral memory of the day in 1995 when I was sitting in my office in the University of Pittsburgh and the phone rang and I picked it up, and on the other end was the director of the National Resident Matching Program, and he wanted to ask if I would redesign the medical match. And I remember having this feeling, you know, gee, I'm sorry I picked up the phone, because I knew why he'd called me. I'd written a book on matching. I had studied the medical match. I'd written papers about it. But in my book on matching, the only thing that was going to directly apply to redesigning the match, none of the theorems would directly apply, only the counterexamples, right? The counterexamples were counterexamples like this one. This is a little better than the one I had at the time. But here's an example, a simple example with 2 hospitals and 3 students there. They're called S, 3 doctors, in which there's no stable matching because 2 of the doctors are a couple, which 2, S1 and S2 are a couple, and they're only the only hospital assignment they'll accept instead of doing something else is S1 goes to hospital 1 and S2 goes to hospital 2. And it wouldn't take you long to check with these preferences that if they're assigned what they want, then there's a blocking pair that involves student 3. And if they're not assigned what they want, then there are blocking pairs involving the couple or one of the students. So there's no way of matching these people so that there's a stable matching. So with a tiny example like this, I had a slightly larger example when I first found one. This one is due to Klaus and Klein. With a very small example, you can quickly show that unlike the case when there are just single people, you can't always find a stable matching. So it's a hard problem. So here I am on the phone. That's all I know about it. And they're saying, you know, we're having this problem. Would you help us solve it? And I agreed to try without knowing how hard a problem that would be. In other words, a counterexample says there could be a very bad problem here. But you don't know that. It could be a rare problem also. So you go in blind. So let's think why the couples problem is hard, though, even if a stable matching exists. Even if when we look at all the preferences, you tell me that there is a stable matching with the couple, the deferred acceptance algorithm is not going to find it. Okay, why is that? The important thing about the deferred acceptance algorithm is when a hospital rejects an offer, they never regret it later. Right? The only time they reject an application, the only time they ever reject an application is when they get one that they like better. And they might reject that one when they get one that they like better still. But they never look back and say, oh, you know, that guy who we rejected a long time ago, it's really too bad we did that. But that's not true with couples, not when you ask them, as you must, for their preferences over 2 jobs. Remember me and my wife. Our first choice is 2 jobs in Boston. So in the worker proposing deferred acceptance algorithm, we first apply to those 2 jobs. And they like us better than other people who have applied, so they reject some other people and they don't reject our application. Now, you are also an applicant in that year, and you get rejected by your first choice. And your second choice is the hospital that's holding my application that I also liked. And they look at your application and they look at mine and they like you better. So they don't reject your application at the next step and they reject mine. Okay? They're never going to regret having rejected mine. But our next choice, my wife and I, we're a couple, our next choice is 2 jobs in New York. So for the algorithm to allow us to apply to our next choice, they have to take my wife out of the position that she applied to, that is holding her application and rejected other people because they liked her better, but she's not going to work there. They have to take her out of them so that we can apply to 2 positions in New York. So the hospital that just lost my wife after having rejected other people so that they could entertain her application, they may regret having done that. There may be people who they rejected, and later they would like to have them back. Okay, so the simple deferred acceptance algorithm, which goes through in 1 pass and never has to go back and correct errors, is not going to work. And so Elliot Parenson and I designed a multipass algorithm. Let me not try to tell you about the flowchart, except to say that on the left is the deferred acceptance algorithm. It's just the thing we saw, except couples are allowed to apply to 2 positions. And if, when I'm rejected from when the job in Boston that had held my offer decides to reject me, my wife is withdrawn from the position that she was holding. And at that time, the algorithm is going to remember it. It's going to put the hospital that had my wife's application withdrawn from it into a hospital stack. And after the deferred acceptance algorithm finishes, it's going to go to the hospitals in the hospital stack and say, these guys may have blocking pairs. They may regret missing some of the people who they rejected. Let's go back and do it again and see if we can fix those blocking pairs. So there's no guarantee that this algorithm will work. There may not be any stable matchings. But one of the things that we notice now in many matches, so the Roth-Parenson algorithm has now been used in many medical matches and other healthcare matches mostly, with couples, year after year, is that it virtually never fails. Let me say that way. I'm prepared to make a stronger statement, but we've run this many times in many years in many labor markets, and even though there are couples, we always are able to find a stable match. So that's a surprise, an unexpected surprise. It's a puzzle that we have to explain, okay, or that we'd like to explain. We knew this before we rolled out the algorithm. That is, we did lots of computational experiments, and we observed that we could always find a stable match. But until very recently, we didn't have much idea of why. That's one of the things I want to tell you about. Okay, so there are going to be 2 empirical puzzles that I'll try to explain there. One is, why do the first one I already suggested, it's why do the stable mechanisms succeed so well, even though it's not always safe for everyone to tell us their true preferences. So although we're producing stable matchings with respect to the submitted rank order lists, maybe they're not really stable matchings. And if they're not really stable matchings, why aren't people getting on the phone, finding the blocking pairs that they're part of, and going to work for them instead of who they're matched to? I'm sorry?
Look back to the previous slide.
Yeah.
What are these clearinghouses? Suppose the man and the woman are in different specialties.
So when they're in different specialties, they can't participate. So the first one is for very young doctors. It's the biggest one. It has all 17,000 American university graduates and another 10,000 foreign ones. Some of the other ones I'll show you are quite small, have a couple of hundred, and may not have any couples, and I'll show you those too in a moment. Okay? So, but you're quite right. What Bob is pointing out is when you find thoracic surgeons, they are seldom married to other thoracic surgeons. There's a thoracic surgeon sitting in the audience here, Jay Levy, who's, I'm guessing, whose wife is not a thoracic surgeon. Okay. I'll tell you about Jay before I'm done. Okay, so 2 puzzles. Why do they work well at all, given that maybe you're not telling us the truth when we ask you your preferences? And why do they work well, even though in many of these markets, but not all of them, there are couples? Okay, so let me start with couples, because we don't have a good answer to that yet. But we're starting to get an answer. So I'm going to tell you about two papers, one by Fuhito Kojima and Parag Patak and me, and one by three Israelis, a better paper, a subsequent paper by Itai Ashlagi, Mark Braverman, and Avinatan Chasadim, who's here also, I think, somewhere. And what we discover, basically, I'm not going to tell you all the assumptions, is that in large markets, if they grow large in an orderly way, as the market gets larger and larger, if the number of couples stays small relative to the size of the market, then the probability that a stable matching exists approaches 1. Okay? So in particular, what the theorem by Ashlagi, Braverman, and Chassidim says is it says in a large random market, if the percentage of couples, the number of single people grows as n, if the percentage of couples goes a little slower than that, then you can, in the limit, be sure that there'll be a stable matching even though there are couples. So that's a better theorem than the previous one. You can't see it there, but we had a more stringent assumption. But it's still not very satisfactory because as you take the limit as n goes to infinity, if the percentage of couples grows slower than the population in general, then in the limit the percentage of couples is 0. And of course, if the percentage of couples were really 0, we wouldn't be worrying about it in the finite markets that we deal with. So this is far from an answer to the question, particularly since they also show that if there's a large enough excess supply of positions, then if the couples grow linearly with the population, then instead you'll get a constant probability that no stable matching exists. So we're starting to get a handle on how large markets with not too many couples, it might not be too much of a problem that stable matchings don't exist, but we're far from having the answer. There's some theorem out there that says if the percentage of couples isn't too great, the probability that you won't be able to find a stable match isn't too large. Okay, and we don't yet have that kind of theorem, but we're getting close. So we're seeing bridges that didn't fall down, and the market for couples works, and we're approaching an understanding of why it works. I can do better on the other puzzle, which is how come, if it's not a dominant strategy for everyone to tell us their true preferences, it's enough to have stable matching mechanisms that are stable with respect to the stated preferences, even though no stable mechanism can make it completely safe for everyone to tell us their true preferences. So to get at the heart of this, why do stable clearinghouses work, even though maybe sometimes someone might have an incentive to tell us preferences other than their true preferences? I want to take you back to another theorem from the 1980s, due to Demange, Gale, and Sotomayor. And it says the only individuals who could possibly profit from misstating their preferences, this is in the one-to-one matching problem, are those who receive different matches, different mates at different stable matchings. Okay, so this can be generalized to models more like hospitals and doctors, but let me take you back to this theorem, because it's from the 1980s. It didn't tell us very much at the time, because you say, oh, look at that. Some people can manipulate their preferences, might profit from doing it, and other people won't. We knew that you couldn't make it possible safe for everyone to tell you their true preferences. This tells you who it might be who can profit. So, but one question you can ask is, how many of these people are there? It sort of gives you an indication that maybe there aren't so many of them, and then maybe it won't be such a big problem. So one of the things we noticed empirically is that the set of stable matchings looked very small. And we first noticed this with the actual medical match data, with couples, with all sorts of complications, that it looked like the set of stable matchings was very small. But one of the things we worried about is, given that there were couples, given that other things were going on, maybe we didn't really understand how to measure the size of the set of stable matchings. So we tried a couple of things to measure them. This is engineering, not science yet. Right? So we tried a couple of things. And one thing we could do is we could look at the match for thoracic surgeons. So thoracic surgeons were a relatively small match. They had fewer than 200 people a year in the years we looked at while we were designing the large residency match. And no couples, right? And they're probably all guys in the 1990s. And what we did in that market, it looks just like the model in Gale and Shapley's paper, that everyone is single. And so we know exactly how to compute the size of the set of stable matchings. We find the worker optimal stable matching and the firm optimal stable matching, and that's it. Everything is in between those. Anyone who's going to get a different match at different stable matchings will get it at those two. And what you see is in some years, there's no difference. There's only a single stable match. In some years, hardly anyone, 1 in 100 applicants are affected. And In other years, no one is affected. So you look at that and you say, this isn't just a limit theorem. I'll show you some limit theorems. We say even in this very small market, the size of the set of stable matchings is very small. And remember, only the people who get different matches, different mates at different stable matches could possibly profit. So in thoracic surgery, the only people who could profit were two programs in 1992 and two in 1993, and none in 1991, 4, or 6 in those data. So you can start to see a glimmer of why maybe things are working so well. In other words, even though you can't make matching mechanisms in general that will give everyone incentives to tell their true preferences, in this one, we've come very, very close to that. And you can't, of course, tell whether you're one of the programs that could have done better or worse by manipulating. Okay, so we decided to do some theoretical computation. We don't have theorems for this, but we have to get a match by 1995. We're doing this in 1994, and we're supposed to have a new match, and we're trying to test whether it'll work. So the first thing we did is we looked at one-to-one matching, a simulation where we understand everything. There are no couples, so we can compute the size of the set of stable matchings, how many people get different stable matchings. And we let n, the number of workers and firms go up, where workers and firms, this is the marriage problem. We're looking at a simple model where it's one-to-one matching. Each firm just wants to hire everyone, one person. And as n goes up, the number of people who get different, the size of the stable matchings goes up. Okay, so when the market gets large, the core gets large, and there's lots of opportunities for manipulation. That's not what we're seeing in our data at all. So we look at our data and we say, how is the medical market large? We say, well, you know, there can be lots of firms and lots of workers, but there aren't lots of days between December and February when you can go on interviews. And so suppose that while the number of firms grows large, the number of interviews that people can go on stays constant. Whatever constant you pick, how many interviews you can go on, and therefore how long a rank ordering you can reasonably submit, what you find is that as the market gets large, the set of stable matchings gets small. Okay, so even when there are no couples, even when we understand all the theorems, we can confirm this unexpected result that we see in the data that the market will be small, and therefore there will be very few opportunities to profitably misstate your preferences, and therefore there will be little incentive for people to do so. Although there are some studies that we heard yesterday at a conference that sometimes even when it doesn't make any sense to misrepresent your preferences, people might sometimes still do that. So there are some theorems about this as well. I'm going to try to finish up. So there are some 21st century theorems that say as the market gets large, if the lists that you can submit in your preference list don't get large, then the set of stable matchings will get small. This theorem is by some computer scientists who were students of mine, Nicola Morlica and Mohammad Madian. There's a limit theorem by Fukito Kojima and Parag Patak that also says in the limit as the market gets large, like that picture I showed you, if the preference lists don't get long, then things will work out. But lately there's also been a very surprising theorem that says, this is by Itai Ashlagi, Yash Kanoria, and Jacob Leshno. It says, you know, why all this concentration on markets where there are the same number of workers and positions? You know, sometimes there might be more workers than positions, sometimes there might be more positions than workers. They look at a simple one-to-one matching market, and what they say is that even a slight imbalance makes the set of stable matching small. So they look at a model with random preferences, but this is the kind of graph they can generate. It says, supposing you're marrying one-to-one matching, you're marrying men to women. If there are 40 men and 40 women, then 60% of the men will have a possibility of manipulating in the women proposing algorithm, because 60% of the men will get a different man optimal stable matching and a different woman from their woman optimal stable matching. But as soon as you go, if there are 40 women, as soon as you go even to 41 men or 39 men, that drops a lot. And as soon as the imbalance gets even a little larger, almost no one can manipulate, because almost no one is getting different mates at different stable matchings. So today, looking back, it's much less surprising that these stable matching mechanisms that produce stable matchings in terms of the stated preferences may not in fact be giving people incentives to misstate their preferences, even though there don't exist any stable matching mechanisms that do that for all problems. Because for the kind of problems we encounter in which people have short lists or in which there can be imbalances in the supply and demand, it's not a problem. Okay? So this resolves that puzzle because the only individuals who can possibly profit from misstating their preferences are those who receive different matches. I'm going to skip over a similar set of events well, actually, before I come to a conclusion here, let me just recap. You know, here's Oman in 1985 saying the relationship between game theory and the complex world is a little complicated. So let me recount the history of that. So in the 1950s, before game theorists had anything to say about these kind of clearinghouses, by trial and error, American doctors developed a clearinghouse that worked pretty well for the environment at the time. And it wasn't until the 1960s that Gale and Shapley, not knowing about the medical matches, explained to us, discovered why matches like these work and made a model of stability and showed that stable matchings were important and could be achieved. And it wasn't until the 1980s that when we looked back at medical matches, we saw that in fact they had anticipated in a practical way, not in a theoretical way, some of these. And that we also started to get some of these results on incentives that presented problems that said, you know, it's going to be hard to get the information you need to get stable matchings because you can't always make it a dominant strategy for people to tell you their true preferences. And then in the 1990s, we got to design some of these markets, and we observed that it wasn't in fact a problem because the set of stable matchings was small. And only now in the 21st century are we getting some new theorems that explain what's going on with couples and why the set of stable matchings is small. And I think this kind of relationship between game theory and market design, game theory and game theoretic engineering, is a lot like the relationship between physics and civil engineering when you're building bridges. That is, we've learned a lot from building bridges about soil mechanics, about metal fatigue, about all the things that cause bridges to fall down, the complicated part of the physics that isn't captured in the simple diagram of a suspension bridge. Now, I spent too much time telling you about this to tell you about school choice mechanisms. Let me just say that in a lot of American cities, they had the kind of problem where they really did make it unsafe for families to tell school districts what their preferences were. In many American cities, they had centralized systems that allocated school places based on the preferences that parents submitted. But if you didn't get your first choice, you often did very badly. And so it wasn't safe for you to tell the city what was your first choice and your second choice and your third choice. Instead, you had to think, what's the best school I can get for my kid if I claim that it's my first choice? The deferred acceptance algorithm fixes that problem because remember how that works. The students in a deferred acceptance algorithm, which we now use in many American cities, it makes it safe for you to give your first choices because if you don't get your first choice, you don't lose your place in your second choice school. It doesn't fill up with people who listed it as its first choice. If they liked you a lot, if you had high priority, you go to the top of their list when you apply to them as your second choice. And so the deferred acceptance algorithm has the property that your chance of getting your second choice school, if you are rejected by your first choice, is just as high as if you had listed it as your first choice. And that's what makes it safe using deferred acceptance algorithms for families to tell school districts what their preferences are. So there's a story there with plenty of broken bridges, but I'm going to skip over that and tell you that in many American cities we now use a deferred acceptance algorithm. But new theory was needed here too, because schools do not have strict preferences over students. Right? By and large, as a political matter, we require schools to treat equivalent children equivalently. Two kids who live in adjacent houses who have the same 7th grade reading scores should have the same access to a city's high school. And so breaking ties, when more kids want to go to a high school or to a kindergarten than it has capacity for, which wasn't a giant issue when we were mostly studying labor markets, became a giant issue for schools, and we needed new theory, 21st century theory, to help understand those issues as well. So tie breaking was important there. So let me start to conclude by saying that there's lots of market design going on in Israel right now. Asaf Ram and Avinatan Chassatim and Ron Shor are deep involved not only in school choice in Israel, but in the market for psychologists in Israel and for medical interns. So there's a lot of work going on here by Israeli market designers. Incidentally, market design, I didn't talk about this here, but the details of how school choice works, the details of how the medical marketplace works are very different here than in the United States. By and large, market design has to be done by local market designers, people who deeply understand the current environment, the current rules of the game. There's also, I didn't talk about, I'll talk tomorrow, some of you may come. I've done a lot of work that I didn't speak about today on organ donation, and one of the big things we've done in the United States is organized kidney exchange. It's now become a standard form of transplantation in the US. And my colleague Itai Ashlagi, his software is somewhere in the Beilinson Hospital, and they've done some kidney exchange. And I mentioned Jay Levy before. He's been instrumental in changing the rules of the game, the Israeli law on how deceased donor organs are allocated. And together with his colleagues and some of my colleagues, we've been studying what's the effect of that in Israel. It seems like it has a good effect. So market design is an ancient human activity, and slowly we game theorists are beginning to understand enough about the design of markets so that instead of doing everything by trial and error, so first we know that the design is important, we can study its effect. But it looks like we may have some kind of game engineering to go with game theory. And, I have to tell you, it doesn't at all seem, it hasn't seemed inevitable to me. But Bob, when he was writing about this in 1985, wrote, what we're trying to do in science is to understand our world. And once we have comprehension, applications are inevitable. So I hope some of you are surprised, but I know that Bob is not, by the practical successes that we begin to have in using game theory as a tool in the ancient human activity of market design. Thank you, Bob.